Hey guys, it's Miss Carlson here again. Today we're going to cover the first two sections of Chapter 10 in Nuclear Chemistry. We are going to cover just what radioactivity is and different types of radiation, as well as how to calculate half-life. So let's go ahead and get started with Section 10.1, which describes alpha, beta, and gamma radiation. Now, radioactivity is the process by which certain elements can emit particular forms of radiation. We would describe an element that emits radiation as being radioactive. Now, there are three types of radiation that an element can emit. One is an alpha particle that are fast flying. They are a combination of 2 protons plus 2 neutrons, which is actually a helium nucleus. If you remember, helium is number 2 on the periodic table, meaning it has 2 protons, and it does also have 2 neutrons. Alpha particles also have a positive charge. Now, beta particles are fast flying as well, but they are actually an electron that is ejected from the atomic nucleus. So because they're an electron, they're going to have a negative charge. And then finally, we have gamma radiation. These are extremely energetic. They are actually a form of electromagnetic radiation, and they have no electrical charge or mass. Now, if we were to use a magnet and a sample of radium along with a lead block for protection, we could isolate these different forms of radiation. And if we were to actually zoom in and look at this, you would see an alpha particle as pictured here. Again, there's 2 protons and 2 neutrons. Remember that a neutron does not have a charge, so the 2 positive charges from the protons will give an alpha particle, again, a positive charge. Now, a gamma ray, again, it is an electromagnetic type of radiation, so it is an actual ray. And then your beta particle, like I said, is an electron, has a -1 charge because there is just one of them, and it is also the smaller particle of radiation. Now, a few other notes about each type of radiation. Since the alpha particles are large in size, they will not easily penetrate solids, but they do have a lot of kinetic energy and can cause some damage to soft tissues. They also will attract electrons quickly to form harmless helium. Beta particles now will move more quickly and are able to penetrate light materials and fairly deep into the skin because they are much smaller. However, if a denser material stops a beta particle, it will just become a normal electron in that material. And then finally, your gamma rays, they are the most harmful because, number 1, they're pure energy, and number 2, they can penetrate almost anything. So this picture here is showing you the penetration levels of each type of radiation. If you haven't noticed the Greek letters here, this letter is for alpha particle, so it would be stopped by a piece of paper. Your beta particle would be stopped by like a sheet of aluminum, but the gamma radiation would still get through, but lead is an element that can actually stop the penetration of a gamma ray, which if you think about it, whenever you go in and get x-rays for maybe your teeth, or if you've broken a bone or something, they usually always put lead vests on you to protect yourself from those types of radiation. All right, now radioactivity is actually a natural phenomenon. If you look at this pie chart here, there is natural background radiation that makes up 81% of the radiation that we encounter in cosmic rays, earth minerals. Then you have 15% from medicine and diagnostic testings, and then 4% comes from consumer products like our television sets, smoke detectors, etc. Now, it's always been a part of the earth and the environment. Some people say that background radiation is actually left over from the Big Bang. Now, that energy is released and is used as heat or to heat water in the Earth's interior. The atmosphere also will help block out some of those cosmic rays so they're not as damaging to us. Radiation can affect the cells, though, that make up your body. Cells can usually self-repair most damage. However, some of the damage that radiation can cause can result in a mutation, and mutations are sometimes harmless, or they could lead to serious problems such as cancer, or be passed on to offspring and possibly cause something else to happen. Now, radon-222, so that's the isotope of radon, is the leading source of naturally occurring radiation. It is found naturally in tobacco smoke and increases a smoker's risk of lung cancer. So just another reason why you shouldn't smoke. And then 1/5 of the exposure to radiation actually comes from non-natural sources like our TV and then medical procedures, as we mentioned from that pie chart. Here's a chart just shows you sources of radiation and the typical relative amount received in 1 year. So you can see cosmic radiation, ground, air, which comes from mostly from the radon, and then human tissues make up the bulk of the radiation that you encounter. So it's natural, it's already in the air. And then human origin would be our medical procedures, TVs, weapons, which is a very small amount. Obviously, most of us don't encounter that kind of thing. All right, now radioactivity does result from an imbalance of forces in the nucleus. And we've talked about the strong nuclear force before. It's a force of interaction between all the nucleons. Remember, a nucleon is a proton plus a neutron. And it's effective only at very close distances. So the SNF and the presence of neutrons do keep those protons together in the nucleus unless they start to get further apart. So you can see in this picture here, a smaller nucleus, the nucleons are closer together. Again, a nucleon is a proton and a neutron. When you get a larger nucleus, you can see how those nucleons are further apart from each other. They get spread out. So the strong nuclear force is going to decrease over distance. A larger nucleus will become not as stable as a smaller one, as I showed you in that picture. And then in order to take care of this instability, that element may decay by emitting high energy particles, the alpha or the beta, or gamma radiation. So a large nucleus with a lot of protons is going to need more neutrons to overcome that repulsive force. And a neutron on its own is going to be unstable. So what will happen is what you see here in picture A, this is a neutron. It will actually break down into a proton, shown in red, and an electron, shown in blue. Okay, and that makes sense because if you think a positive charge and a negative charge, they cancel out to make that neutron. So what's going to happen is that electron gets ejected as a beta particle, and then you are left with the proton in the nucleus still, or you can have an emission of an alpha particle. So any atom that has a number higher than 83 is considered radioactive because the nucleus gets so large with neutrons and protons that the strong nuclear force cannot hold in those particles. All right, guys, the last section we're going to talk about is 10.2, rates of nuclear decay. If you have a shorter half-life, you will actually have greater radioactivity. And radioactive isotopes, they all decay at different rates depending on the element type. And a half-life is technically defined as the time needed for half of all the radioactive atoms in a material to decay. Now, radium-226 takes 1,620 years to go through one half-life. And keep in mind that half-lives are not affected by any external conditions. They are what they are, and they do not change, except for the fact if you're talking about a different element. So if we were to look at radium-226, a sample right here, we have a sample mass in kilograms. So if we were just talking about 1 kilogram of radium, it would take 1,620 years for half of it to decay. And then for another half, take another 1,620 years, or a total of 3,240. And then again, another 1,620 years, or a total of 4,860, we would have 1/8 of 1 kilogram of radium left. So half-life depends on the element, and it can range from 1/1,000,000th of a second, so really, really quick, or even to 4.5 billion years. There is also something called isotopic dating or carbon-14 dating, or even known as radiocarbon dating, that can measure the age of a material, which is useful for many scientists in different areas of study. But all plants contain a tiny quantity of radioactive carbon-14, so all animals do as well. And when a living organism dies, the percentage of carbon-14 decreases at a constant rate that we call half-life. So the half-life of carbon-14 is actually 5,730 years. And we could look at an organism that had passed away 22,920 years ago and identify it using our knowledge of carbon-14. So again, we call this carbon-14 dating. there is a 15% uncertainty when scientists identify the age of an organism, but it definitely gives us a rough idea. Now, I'm going to stop there. We're going to talk about artificial transmutation and nuclear fission and fusion next time. So go back and pause, replay anything that you may have missed. Make sure you took good Cornell notes, and I will see you guys next time.